we notice that the fundamentals, the thing at the very, very basic core of AI, has not changed in 50 years. 50 years.
In short, we're ready for what Thomas Kuhn described as a paradigm shift. We've had the same fundamental Ising equation underlying all energy-based neural networks for 50 years, and we've about pushed the limits, so perhaps we're ready for something new.
And it's fairly obvious as to why. When we take a look at the literature and go beyond the ooh, wow, gee whiz stage of things, like you can get a GAN to do this, and you can get, something else to do something else, and the list goes on, and there's all kinds of fabulous applications being developed. Not dissing this at all, really fabulous applications. We notice that the fundamentals, the thing at the very, very basic core of AI, has not changed in 50 years.
This slide shows us the evolution of energy-based neural networks over the past 50 years. We're going to use this as a baseline for finding the breakpoint at which we went from Kuhnian breakthrough science to Kuhnian normal. Let's start with where modern neural networks began in 1974. Now, we do want to bring this conversation up to speed by including transformers. However, if you take a look at a really beautiful series of blog posts by Matthias Ball, and the links to that and the full references are in the associated blog post, see the link in the description box, you'll see that transformers are, in a sense, grown up versions of the Ising equation, where the simple scalar spin of an individual unit is replaced by a vector spin. We're going to use the simple Ising equation as a baseline for our discussion and then expand in future vids. Let's take ourselves back a step in time to where this all began.
1974, let's talk about what happened. 1974, Paul Werbus presents his dissertation, and in that, he presents the backpropagation method. He didn't become well known for it until 12 years later, when we had the first neural network conference. It was the International Conference on Neural Networks. And for the very first time, neural networks practitioners who've been tremendously isolated, socially, intellectually, every possible which way, they came together, and they had not only a meeting of minds, but a sense of identity as a group that had never happened before. A new journal was launched. Just prior to that, there had been a 2-volume book that brought together very significant works, which launched the interest in this conference and in neural networks overall. 1986, 1987, 87 is when that conference happened, was really the kickoff of neural networks as an engaged research area. So Paul didn't really start to get a lot of recognition until around then. Simultaneously, you had the West Coast players. Now, John Hopfield was included at that time, Hopfield Neural Network, energy-based neural network. His work, published originally in 1982, was actually based on the work of William Little, 1974. So 1974 is the genesis year for the two most important contributors to neural networks as we know it today, meaning not just the Hopfield neural network, which was a predecessor neural network, and Hopfield's great contribution was identifying essentially its limitations, the limits on how many patterns you could hold. But then the introduction of latent variables, which is Hinton's great contribution, began to make this a robust, workable neural network. And for a while, multilayer perceptrons trained with some variation of a backpropagation-like method, and Boltzmann machines, which were Hinton's contribution, were sort of neck and neck. In fact, I, at that stage, kind of thought they were equivalent mechanisms. I was wrong. Boltzmann machines, using an energy-based approach, it's the same equation that Hopfield used, and of course, William Little ahead of him. And ever since then, and here's the important thing for all of us, ever since then, everything that has been an energy-based neural network, meaning, of course, Hopfield, Boltzmann machine, the restricted Boltzmann machine, all forms of deep learning, all forms of GANs, everything that makes a GAN or a deep learning method workable, meaning all of these transfer functions and diffusion methods and such. Anytime you start stacking the layers,
And I'll say this is specific to deep or generative types of architectures.
You're going to use some form of a Boltzmann machine in there because that's what gives you these latent variables that act as the inputs to the next layer. It's all the same equation, okay? The very same equation is percolated through 50 years, 1974 until now. The fundamental equation hasn't changed.
And yes, we do want to acknowledge that the transformers are a big step. However, it's still the Ising equation. We're just creating vector spins where previously it was just scalar.
That means that we are stalled. We're stuck. And we can do applications until the cows come home, but they're applications, they're refinements. If we were to use the terminology of Kuhn, like, normal science and then breakthrough science, we haven't had a paradigm shift since about, I want to say 87, 86, 87 with the Boltzmann machine. That was a paradigm shift where introducing latent variables made the Hopfield workable, and the whole neural network, creating those deep layers, that's been Kuhnian normal science. A lot of hard work, a lot of effort, a lot of, creative, very insightful thinking has gone on into making it work. A lot of computer power, a lot of data, but it's just making work. Something that was invented essentially as a workable system in 1986 and using equations that were developed in 1974. We've said enough today. I'd like you to have a moment to consider. In the next video, we're going to bring in the notion of what problem statement is this neural network solving, because that's going to give us insight. We're going to look at the problem statement behind backpropagation and the multilayer perceptron. We're going to look at the problem statement behind the energy-based systems. Essentially, we'll just look at a Boltzmann machine, knowing that whatever we evolve beyond that by stacking layers or having them compete is a variation on that theme. And I want to introduce a different researcher, Steve Grossberg. We want to talk about the problem statement behind his work because it is so different that as we begin to step back and absorb how the problem statement leads to the architecture and the functionality and the benefits, we'll get a broader perspective because we need to be opening up our perspective. That time has certainly come.
As a little postscript, one of the papers that we'll consider when we do our analyses of different problem statements is take a look at Hinton's forward algorithm, his latest algorithm designed as a replacement for backpropagation. One of the reasons that we're interested in this is not only the algorithmic nature itself, but also the way that Hinton is phrasing his problem statement is as a brain science perspective, not just statistical mechanics. That alone makes this interesting. We realize that you may not have the background in statistical mechanics that you'd like to have, especially of the Ising equation. Themsys is offering a 3-week short course. Please go to themsys.com, hit the About menu option, do the opt-in, and we'll certainly let you know. Also, we'll be making announcements via YouTube and LinkedIn. With these YouTubes, please do the like, subscribe, and hit that notify bell, and we'll let you know not only when there are new YouTubes, but also blogs and other useful materials. Thanks for joining us. Have a lovely day. This is Aliana Moren from Themsys.